Good day, everyone. My name is Alina Jade Haring, and today I'll be discussing my mini pitas number one. So, the situation is all about the pilots at an air show perform a loop the loop. The pilots are oriented upside down at the top of the loop. Explain why they do not fall out and what is their natural tendency while in circular motion. So, to answer that, when aviators execute a loop the loop during an air show, one may ponder why they remain securely within the aircraft. Even when positioned upside down at the loop zenith, the explanation lies in the fundamental concept of centripetal force, which is the force responsible for keeping an object on a circular trajectory. As the airplane completes the loop, centripetal force acts toward the center of the circular path formed by the loop, ensuring the continuous circular motion of both the pilot and the aircraft. This force originates from the lift generated by the aircraft's wings, remarkably at the apex of the loop. Despite the inverted orientation, the wings continue to produce lift in the downward direction, effectively counterbalancing the gravitational force. And moreover, pilots are securely fastened into their seats during harnesses and frequently don specialized fly suits designed to withstand the gravitational forces encountered during aerial maneuvers. Their inherent inclination is to adhere the loop's curvature due to the centripetal force, and as long as the equilibrium between lift and gravity is maintained, they remain safely enclosed within the cockpit. So that's all. And this is the SS or a screenshot of my script plagiarism checker. That's all. Thank you. Good day, everyone. My name is Alina Jade Haring, and this is my mini pitos number 2 that talks about Kepler's 3 laws of planetary motion. So, step into the captivating realm of Kepler's 3 laws of planetary motion, a celestial masterpiece that revolutionized our comprehension of how planets elegantly traverse the cosmic arena. So, in the early 17th century, the brilliant astronomer Johannes Kepler unveiled these laws, unraveling the enigmatic patterns of planetary orbits. These groundbreaking work challenged age-old concepts, laying the foundation for a transformative era in the astronomy. So, picture a time when the cosmos posed a formidable puzzle for astronomers who grappled with deciphering the intricate ballet of planets around the Sun. Kepler's profound insights emerged as the key to unlocking the celestial choreography. Through his meticulous observations and mathematical brilliance, Kepler disclosed a trilogy of laws that not only delineated the trajectories of planets but also reshaped the very fabric of our understanding of the universe. Embark with us on this cosmic odyssey as we unravel the grace and significance encapsulated in Kepler's 3 laws of planetary motion. Here, elliptical orbits, sweeping areas, and mathematical harmonies converge to weave a mesmerizing narrative of our celestial companions. In the initial law, Kepler proposed that planets follow elliptical orbits with the Sun positioned at one of the foci. It is crucial to underscore how this departure from the earlier belief in perfect circles represented a pivotal shift in astronomical thinking. Moving on to the second law, it is clarified Kepler's statement that a line segment connecting a planet and the sun sweeps out equal areas during the equal time intervals. This dynamic principle underscores the variation in a planet's speed as it moves along its elliptical orbits. Lastly, explore Kepler's third law, which correlates the square of a planet's orbital period with the cube of its semi-major axis. Elaborate on how this law establishes a mathematical connection between the duration it takes for a planet to complete an orbit and its average distance from the Sun. And that's all. So this is my screenshot of the plagiarism checker. That's all. Thank you. Good day everyone, my name is Alina Jade Haring and today I'll be discussing the Mini Pitos number 3. So the story began with an apple falling on his head, sparkling curiosity about the Earth's gravitational force. During the Great Plague in 1665, Newton isolated himself in the countryside, developing the mathematical framework for gravity. He envisioned a universal force between any two objects, leading to the formulation of the law stating that every mass attracts another with a force proportional to their masses and inversely proportional to the square of the distance between them. It is F equals G times M1 times M2 over R squared. This law explained not only earthly gravity but also became a fundamental principle for understanding celestial motion, laying the foundation for classical mechanics and physics. So, this is the question. Suppose that two objects attract each other with a gravitational force of 16 units. If the distance between the two objects is tripled, then what is the new force of attractions between the two objects? So, Newton's law of universal gravitation states that the force of attraction between two objects is inversely proportional to the square of the distance between their centers. The formula for gravitational force is given by this. So this is the formula. So the gravitational force is equals to the fraction G over C dot times M1 over M2 R squared, where the G is the gravitational constant and the M1 and M2 are the masses of the two objects and R is the distance between their centers. In this case, let's assume that the masses M1 and M2 and the gravitational constant G remains constant. If the initial force of attraction is 16 units and the distance R is tripled, then the new distance becomes 3. Now, we can use the inverse square relationship to find the new force. F equals frac G C dot M1 over C dot M2 3R squared. Simplifying this expression would be F equals frac G C dot M1 over C dot M2 times 9 over C dot R squared. So the new force of attraction would be 1/9, or the initial force. Therefore, the new force is fraction of 16 9 units. So that's all. Thank you.
Hi, my name is Amir Jonas Dikakidi. I'm here to enjoy the amusement park.
Hey there! Welcome to Amusement Park. Today, I'll be your tour guide for today's adventure. I'm here to talk about the cool science behind one of our exciting rides that spins in a circle that can make you throw up if you have a weak stomach. Hey Jonas, come closer. Are you a fan of spinning rides here?
Yes.
Fantastic! Now, did you ever think about why you get that giggly feeling when you're on a ride that goes in a circle?
No.
Well, that's where the wonderful world of physics adds its special touch. Well, it's all thanks to physics. Picture yourself on a ride like a carousel. As it begins to twirl, have you ever felt a nudge towards the outer edge? It's like a friendly push, isn't it?
Yes.
Well, that's all thanks to something called centripetal force.
What is it?
So, centripetal force is the inward force that keeps an object moving in a circular path, directed towards the center of the circle or the axis of rotation. So, let's move on inertia. Picture this. When the ride starts, you and the seats are just chilling, not moving, but as the ride speeds up, your body kind of wants to go on a straight line. Yet the ride keeps tugging you towards the center with centripetal force, leading you on a merry journey in a circle. Now, here comes the exciting part. Even though your body is itching to go straight, the ride keeps pulling you towards the center of centripetal force. It's like a playful dance between your body's urge to go in a straight line and the ride's force, making that super cool circular motion happen. So, Jonas, the next time you're on one of these awesome spinning rides, just remember the magic of centripetal force and inertia, making your adventure so thrilling. Have a blast at the amusement park.
Thanks. Bye.
Bye!